Okay, so welcome to week three's problem solving session. Uh, Today we'll solve week three's problem, some problems related to week three's assignment. And since the deadline for the first two assignments has passed, we'll also look at some of the questions from those assignments. Okay, yeah. So let's first quickly recap what we saw in this week. So, so we have been looking at theorems that give us lower bounds for formula size. And last week we saw Kharchenko's theorem and Nechiporov's theorem. And this week we saw Subotovskaya's theorem. And the theorem says the following. It says that for any Boolean function f from 0, comma 1 to the n to 0, comma 1, uh, the expected value of the size of f sigma is at most epsilon to the 1.5 times LF plus 1 over 3. And over here, sigma is a restriction, which is picked uniformly at random from this set. And this set is a set of all restrictions, which leaves only epsilon and variables untouched, right? So all variables other than epsilon and many variables would be set to some values. Then we also saw some applications of this result. And the first application was sort of a toy application. We proved that the formula size of parity is omega n to the 1.5. We already saw a lower bound of n square using Kharchenko's theorem. So this is strictly weaker than what we were able to get from Kharchenko's theorem. And moreover, the lower bound that you get from Kharchenko's theorem is actually tight. Yeah. So that bound is much better than this bound. But then we also saw another bound, which was for Andrew's function. And we saw that a lower bound of omega n to the 2.5 minus epsilon for any epsilon greater than 0. In fact, the lower bound was n to the 2.5 over some powers of log, right? And this is much better than the lower bounds we obtained from Kharchenko's theorem and Nechiporov's theorem, which were like quadratic, right? And in one of the problems last week, we also saw that both of those lower bound techniques cannot give you anything better than quadratic, right? So, Subotovskaya's theorem is strictly more powerful than Kharchenko's and Neshiporov's theorem in this sense that it can give you better lower bounds than quadratic. And finally, we saw Valiant's proof that there exists a monotone formula of size order n to the 5.3 and depth 5.3 log n for majority. Okay, so this is what we saw in class, and now let's look at some of the problems related to this content. Okay,
Uh,
yeah.
One thing. Could you walk us through the proof of like Valiant's proof for majority? Because like individual claims are clear, but how does all of those overall tie up together is a bit confusing.
Yeah, so even I don't properly understand Valiant's proof.
Okay, so maybe at
Yeah,
the end of lecture we may just take a look at it.
yeah,
Would that be okay?
yeah. So at least at the very high level, what's happening is this. So you have a random construction, right, of a
Right.
formula,
Right.
right? Now what you are showing is, uh, okay, start from the bottommost level and gradually move towards the root, right? And for every level you move, you become closer to majority.
Closer in the sense.
Okay, I think it's closer in the sense that I think the number of x's for which your function agrees with majority increases.
Okay, so my output may agree with majority or may not, but probabilistically we are trying to show that it is possible,
Right. So
and
the
that probability
probability,
increases as we go up.
right?
Okay.
Yeah.
Okay, like if we have time, then I think we should like to like go on a bit more about it. So
Yeah. Okay. So yeah. So the first problem is about monotone functions, and I think we'll also see monotone functions later when we prove monotone formula over bounds. Yeah, so the problem is this. Hmm, yeah, so we want to show that any monotone function can be computed by a monotone circuit, and a circuit is said to be monotone if it only contains and or gates. Okay, so yeah, would you like to suggest how we can go about doing this?
Uh, like, can be computed only using AND NOR gate, right?
Yes,
You didn't mention by a monotone circuit. Okay, so the argument is simple. Like, if the function should remain high if we are flipping a 0 bit to a 1 bit, right?
right.
So suppose we have a B string and all of the bits are zero, then only if we are taking OR of it, it would be zero. If we flip any bit to one, the output changes to one, and further changing any bit to from zero to one, the output would remain one. Right?
Okay,
So OR I think follows monotonicity by this type of argument, and similarly for AND, uh, if all of the bits are not one, like if there is some bit which is zero, right, the output remains zero, and only when all of the bits are like set to one, then only the output becomes one. So
okay.
when at the final string, uh, am I audible or did I break?
Yeah. So you're audible, but what I'm not able to understand is how does this prove that every monotone function can be computed using just and or gates?
Okay,
So
so
that's what we want to do, right?
okay, every monotone function should be computable by these two functions.
Yeah. So a monotone circuit is just a circuit that contains only and not gate and or gates. So the
Right,
question is saying show that any monotone function can be computed by using just and or gates.
right, right.
Okay. So right now, okay, the question does not say anything about the size of the circuit. Like,
Yeah, it doesn't.
yeah, so we are okay if it's very large. Okay. Now, in in the setting where we are fine with very large circuits, we know of a circuit using and or and not gate that computes any function, right?
Right.
And what do we do in that circuit?
Like we replace not using and or, I think.
No, no, no. Okay, that's not possible because if you could do
Uh,
that, then every function you can
no, no,
compute
no.
every function using just and or gates, right?
Right, right,
Right. Okay, so okay, what do we do in that circuit? So forget about monotone circuits for now. Let's
right.
just try to compute any function using just and or and not gates, right? So what does
Okay.
that circuit look like?
Well, what do you mean by like what does that circuit look like? I'm just not getting what you're trying to get at.
Okay, so what I'm trying to do is we'll first look at what the circuit looks like and then see if we can remove NOT gates from there.
Okay, so that circuit would be kind of a tree, a binary tree.
Okay. For now, let the fan-in be arbitrary.
Okay.
Yeah. Then
So
it would.
it is a graph. Is that like?
No, no. Okay. So what I was getting at is there is a CNF or a DNF for that circuit, right?
Okay.
For that
Yes.
circuit,
Yes. Yes.
right?
Yes.
So
Right. Yeah.
that's what I'm saying. But stop worrying about fan-in. So you can
Right.
take arbitrarily like fan-in, like arbitrary fan-in and an OR gates,
Yes. Yes. So we would have a
right?
CNF or a DNF.
Right. Like, okay, so let's say we want to do all of and, so it's a DNF. Okay.
Right.
So what would we do for every x? So that f of x equals 1, we'll pick that x and create an and of a bunch of things for it, right? So for every x, so that f of x equals 1, we have one AND gate. Then what does that AND gate do? If xi equals 1, then the input is xi. And if xi equals 0, then the input is xi complement, right?
I think I lost it somewhere
Okay,
in the between. Could
right.
you
So
please repeat it?
yeah, so we have a DNF, and in that DNF, what we are going to do is we are going to have an AND gate for every B such that f of B equals 1. Okay, so
Like we have a DNF, it is an OR of ANDs.
right, and so okay, right now we are trying to construct that DNF, right?
Okay.
So that's an OR of ANDs. What I'm saying is, in the way we are going to construct it is as follows: for every B such that f of B equals 1,
Right.
we are going to have an AND gate corresponding to that B. Okay. That
Okay.
AND gate is going to do the following. If Bi is for some I in 1 to n, if Bi is 0,
Right.
then that AND gate, like one of the children of that AND gate would be not Xi. And if Bi is 1, then the child would be Xi, right? So
Yes.
what this AND gate is going to do is it's going to be 1 if and only if you feed in Bi.
Yes.
Okay. So over here, okay, we have NOR gates, right? What are the NOR gates doing? Suppose you were to remove a NOR gate, what would happen? Okay, let's take a simple example. Suppose n were 3 and b was 0, 1, 1. Okay,
Okay.
then, and like what would the AND gate for it look like? It would look something like this, right? And not x1, x2, and x3, right?
Yes. Yes.
Suppose I were to remove this AND, what would happen? What can go wrong?
Oh, like if you're removing that knot, right?
Right.
So for 0, 1, 1, it would give output 0, but for 1, 1, 1, it would give output 1.
Oh, so for 0, 1, 1, it would give 1.
Okay, you're removing the entire like subtree or what?
Yeah, yeah. So I'm removing the thing that I circled, not x1.
Okay, okay.
Yeah.
So for any value of like x2, x3, when both of them are 1, it would output 1.
Right. So what can go wrong is the following. Suppose f of 0, 1, 1 was 1, but f of 1, 0, 1, 1, 1 was 0, right?
Right.
Then our circuit would compute the wrong function.
Yes, yes.
But notice that this can never happen in a monotone function, right? If
Yes.
0, 1, 1 evaluated to 1, 1, 1, 1 must evaluate to 1.
Yes.
So what you can do is basically forget about checking all zeros.
Okay.
Yeah,
So we can only consider the ones in the string and like
right.
use that.
Yeah. Okay, so now let me just do this more formally. So, yeah. Okay, so what? Okay, so we have this, right? X equal less than equals to y if and only if for all I, xi is individually less than equals to yi. And what do we have? If for all x comma y pairs, if f of x is less than equals to f of y, then sorry, if x is less than y, f of x is 1 implies f of y is 1, right? So this is just the definition of monodromy function, and now we can start constructing the circuit. So the way we'll do it is S be the set of all E in 0, comma 1 to the n. So I'm assuming the function is invariant such that f of b equals 1. Let C be all over b in S and over all i's such that bi equals 1, etc. Yeah, so this is the circuit. And now what's the claim? The claim is C computes F. Okay. Okay. So what does it mean to say that C computes F? It just means that for every y, C of phi is the same as F of phi, right? So so we need to show that for every y, C of phi is F of y. So there are two cases, right? Okay. For okay, so in this case, I want to argue that C of y is also one. So how can I do that?
You can like we can construct the circuit using the truth table where by using NOT gates, and after that we can remove those like
Oh, so
separate
we have
switch
already
nodes.
constructed. Okay, so what we have done is we have already constructed that circuit over here. So this
Okay,
is exactly that, right? For
right,
all y's that so for all b's that f of b is one, we have this gate. So
right.
we have
So
already constructed the circuit, and now we want to show that this circuit computes f.
okay, since the inputs are one, uh, the AND should always output one side. Like there are no zeros input to the AND gates.
Right? Okay, but
So
wait. Why are there no zeros input to the AND gate? Suppose there might be zeros input to the AND gate, right? Because okay, so it's B in S. For every B in S, you have this gate, right?
alright,
Wait, did I? No, no, I think it's fine. Yeah. For every B in S, you have this gate. So suppose that 0, 0, oh, sorry, suppose 0 to the N was not in S, right? Then
right.
when you plug in input 0 to the N, these gates would start, some of these gates would start getting 0 as inputs, right?
Yes, yes.
Right. So this circuit, it's not the case that this circuit is always 1. Otherwise, you would be in trouble, right? Because then this computes the all ones function and not F.
Okay. So, like, I get the idea how you like explain that how we can create a monotone circuit by
Right.
not considering the inputs which are like which go to zero. Uh, but like, can you just once again explain this argument? Let C equals to R over like B belonging to S. Like, what does this exactly mean? Like the AND part, what is it? I equals to one.
Okay, right. So if I were to write a circuit for any arbitrary function, okay, not a monotone function, what would that circuit be? Okay, yeah, this is too much trouble. Just let me write it. For all B in S, uh, and okay, what's the best way of writing it? Yeah, I think the best way of writing it is this.
Is that
And
we would have and for x's which are like one, it would be like just itself, and for others it would be negated.
yeah, so if like that circuit, the expression of that circuit would be this, right?
Right, right.
Okay. Now, okay, suppose you, now what we are doing is we are just removing this part, and that gives you this expression. Okay, so first, are you convinced that this is the circuit that you, that we discussed in the like informal overview,
Yes, yes.
right? So now what we want to argue is, so we informally argued that this circuit computes F. I want
Okay,
to do the following.
just
Okay,
one
yeah,
thing. Uh, like B as a string of length n, right? Just a string,
right,
such that the function outputs one on it.
yes,
So okay, it's just a truth table. We are taking all over such B's, right?
right,
Okay, okay. Now I get it completely.
yeah, yeah. So if you're convinced that this is the circuit
Right.
that we discussed, then now can you tell me? Okay, okay, so now what I'm trying to prove is C computes F, and the way I'm doing it is look at two cases. Uh, First, we'll look at all y's for which this is 1. So, sorry. First, we'll look at all y for which f of y is 1. And then we'll look at all y's for which f of y is 0. And we'll show that in both cases, c of y would be 1 and 0 respectively. And that would mean that for all y, f and c are the same. And so they c computes it, right?
Right, right.
So now what I'm asking is, I have fixed the y so that f of y is 1. Now, can you prove that this expression is going to be evaluated to 1 when I plug in y? That is, c of y is 1. How would we argue that?
Okay, so we know that this the function on this input gives one. We need to show
Right.
that the circuit would also give the output one.
Yes.
Okay, so we go about doing that.
So this is an OR of AND, right?
Right.
So even if one AND were one, we would be done.
Yes.
So can you tell me, can you find out one AND gate which would be one
Uh, one NAND gate should be one.
when I plug in Y?
I didn't get this. Like one NAND which should be one. What do you mean by that?
Okay, so this circuit is an OR of AND gates. I want to show that this
Right,
circuit
right,
is one, right?
right.
So even if I can show that one of these AND gates evaluates to one, when I plug in Y, I'm done, right?
Yes, yes.
Yeah, so what I'm saying is, can you find one AND gate which would be one when I plug in Y?
So you can set all of them to one. Then it would be also one.
Okay, but how do you set an AND gate to one? By plugging in the input, right?
Yes, both inputs to one.
No, 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 no.
Uh,
Okay, so this is an AND gate.
Right.
How would I make this AND gate one? So xi is over here, xi is a variable, right? I would have to plug in some value for xi, for every xi,
Yes, yes.
right? So the way I would make an AND gate one is by plugging in the right values of xi, but that I don't have complete control over it, right? So I have already said over here that xi equals yi. Okay, so what I'm saying is this AND gate becomes one. Okay, okay, to make this AND gate anything, 0 or 1, you would have to plug in some values, right?
Yes, yes.
And so okay, so this is C. So what, okay, let me write it like this, C of X. So C of X is this, right? Now, I want to show that C of Y is 1. So what would X become?
Why?
Right. So now what I'm asking is, can you show me one gate so that that gate would be 1 when I replace Xi by Y? We already know that F of Y is 1.
Okay.
So, okay, so the argument is this. You know F of Y is 1, right? So Y is in S, right?
Yes, yes.
Right. Uh, and Yeah, so Y was in S, and because of that, there should be one AND gate corresponding to Y, right?
Okay, yes.
And what would that gate look like? It would look like this. So over here, you have a gate corresponding to B. If I replace B by Y, then this is what the AND gate becomes, right?
Yes, yes. So,
Yeah,
like we can say, let's say we have an OR gate at top and we have AND gates for all the as many AND gates for as many values the function outputs one
right.
for the truth table, and for each of the AND gates, it's the corresponding string is the input which gives the output one. And for the
It is one
string,
of the inputs that gives it makes it one.
uh,
So in
I'm
this case,
assuming
you would
the
be right.
circuit. I'm assuming the circuit in three layers. The topmost is an OR, the second layer is an ANDs, right? And number of ANDs are exactly the number of, uh, like let's say F inverse one,
Okay, right,
right? And each of those AND corresponds to each of those individual input X for which the function should output one. And it's not all the X bits; it's only the bits of X which is one, right?
right.
So like by that argument, if you're saying f of y is equals to 1, then it means that it is one of those ants among the tree which has got this particular y as its input.
Okay, so I don't understand your question. Y is fixed.
Yes,
So
yes.
we the
So
way we
this
have
is
fixed Y
basically
is f of
searching,
Y is
like
one.
finding, like I don't know why this like argument was a bit confusing, but it's simply like by the construction of the tree itself, such a y
Right.
must exist as an
Yes.
input to one ant. You take
Right.
any
So
y, right?
the moment you figure this out, you are done, right? Such a Y must exist. Such an AND gate must exist.
Yes, yes.
Right.
Okay. Yeah.
Yeah. Okay, but however, this AND gate can evaluate to one even though the input is not Y, huh?
Yes, like it might be possible that some bits of y are like flipped to zero. That also may exist as an input to some
Right.
other AND gate.
Yes.
Let's say function
So
is constant, one like outputs one for all of them.
right.
So,
Yeah, so I was trying to point out the difference between these two circuits. So over here, corresponding to a Y, there is a AND gate, right? And that AND gate is one if and only if you plug in Y.
right. Yes, yes.
Over here, corresponding to every Y, there is an AND gate. That AND gate is one when you plug in Y, but it might also be one when you plug in something else.
Yes, yes.
Yeah. And I think that will help us in the second case. Okay, that might be an issue in the second case. Okay, so the second case is f of y is 0. So over here, what do we need to show? We want to show that c of y is also 0.
Right. So would we show that like for every each of those AND gates, at least one of the input is zero?
Right. So every AND gate is 0. Right.
Yes. Yeah.
Okay. So, and how would you show that?
That's what I'm thinking. But
Yeah.
so y is not in S. That's
Yes.
okay. Like, could you give the hint, some hint about the argument? Like,
It's by contradiction.
it's by contradiction.
Yeah.
So suppose we assume y was in S, then at least one of the gates would output one.
Okay. No, y is definitely not in S.
Okay,
It
y
is
is
given the definition of
definitely not in
S.
S.
S is just f inverse 1.
Okay, yes, yes.
Okay. So what do you want to prove? You want to prove that every AND gate is 0, right?
Right.
So
So I
the
assume some
contradiction would
AND
be
gate
there
is one.
exists an AND gate which is 1.
Right.
Right.
So if I assume there exists some AND gate which is one, that
Right.
means the input corresponding to that AND gate should be in S.
Right.
And we have like we have from the definition itself that a y is not in S.
right?
So is this the contradiction? Like,
No, it would have been the contradiction if the circuit were this,
okay, yes, yes.
right? Because let's say that that AND gate corresponds to B. Over here, that AND gate would have been one if and only if you plugged in B. But over
Yes,
here,
yes.
the AND gate can be one even in other cases, right?
Different inputs can like make the same and get one.
Right. So now you need to find out some relationship between B and Y.
Oh, P and Y. Okay.
Yeah. Okay, so let me write down like what we have discussed so far. So wait. So, so the gate looks like and xi, right? So when I'm talking about C of y, I should replace xi with y, right? Yeah. So suppose by contradiction that there exists a B in S that and I in I say that Bi equals one, Yi is one. Okay. So now can you tell me about any relationship between B and Y? B and Y.
So any string in B, like any string, okay, B and Y.
Okay, so this is one and gate is one. What does that tell you? And when is an AND gate one?
Well, all the inputs are one. Okay.
Right.
The
So what does this tell you? For all I such such that Vi is one, Yi is also one.
right.
And what does this mean?
It is okay. So expression.
So for all I, Xi is less than Yi, right? Okay. So, okay. Let me do one more step. So, this implies that for all I in N, Bi is less than equals to Yi. Why? Because there are two types of I's, right? Those that are in S and those that are not in S, right? For those that are in S, Bi and Yi are both 1. For those that are not in S, we know that Bi is 0, right?
Yes, yes.
Uh, okay, no, okay, wait,
And for Y,
not
it
in
might
S.
be 1 or 0.
Yeah. Yeah, so that means whenever, okay, so when for every I, Bi is, if Bi is 0, Yi can be anything. But if Bi is 1, Yi has to be 1. So for every I, Bi is less than equals to Yi, right?
Yes, yes. And by
Right,
the definition of a monotone function, yi must
right.
also output 1. So y
Yes,
must also like go to 1 since b
right.
goes to 1.
And this is a contradiction, right?
Yes, yes.
So no such V exists. Yeah, so all AND gates output zero, and so CY is zero, right? Yeah. Okay, so this finishes the first problem. Second is sort of complementary. So over here we show that every monotone function can be computed using and OR gates, right? The second problem is to show that,
One thing,
yeah,
are the set of monotone functions and the functions computed by and OR gate, like, are
yeah, that's the
they
next question.
okay? Sorry.
Okay, computed that, let me write it in a much cleaner. Show that any function that can be computed. Yeah, so this answers your question, right?
Show the right, right, and the other
Right.
direction is above. So,
Yes. Okay, so okay, how would you, okay, like, would you try to come up with some argument about how to show this? In fact, if you remember at the beginning of this question, first question, you
right.
you gave some argument, right?
Yes, exactly. I tell the gates themselves are monotone.
Right. So
So any circuit
using that
using those
argument,
gates would also be
yeah. So using
monotone.
that argument, can you show that this question is true?
So, well, the overall argument would be like the gates individually are monotone. So you
Hmm.
combine them in any way, the output, the resulting function would also, the circuit which we get using that would also give the resultant, would be computing a function which is monotone in nature.
Right. Okay. So how would you argue that and okay? So okay, another way to frame this argument is, okay, should I do it? Okay, yeah. Let me just do it like this. So you are
I
claiming
think,
that uh, if you combine a bunch of monotone functions using
right, right,
and OR, you get a monotone function, right?
right, right, right.
So okay, how would
Yes.
you argue that?
Yes, yes. I thought you would ask, like, because the gates
Yeah.
are individually monotone and I'm combining them. So the combining function, like the this operation should also retain monotonicity, right?
Right. Exactly. Just give me a second.
Okay.
Yeah.
So
Okay.
again, like
So
if I have a
yeah.
monotone function and it is an input to a OR gate,
Hmm.
uh, any like what do I say? Any input, like suppose, uh, I what do I have to show? Like, if the inputs to an OR gate are monotone, the output should also be monotone.
Yes.
Okay.
Okay. So
So
yeah. Let me write down some other things till now. The proof will be by induction. Okay. Yeah. So what we're going to do is we're going to prove this by induction on the size of C, where C is a monotone circuit that computes F, right? What we want to show is that F is also monotone, is a monotone function. And okay, one way to do induction is like by on size of C, and the base case would be C has size 0, right? So C has no gate in it. So if C has no gate in it, F must be Xi for some I in L, right? Okay, I forgot. This is not the only case, or 0 or 1. So if C has no gate in it, then F must be either a variable or a constant function which is always 0, or a constant function which is always 1, right? And all these three functions are monotone. Is this fine? Yeah. So now let's look at the induction step. In the induction step, what we are going to do is we are going to assume that this is true for all functions computed by monotone circuits of size less than size of C, right? So from this, okay, so first of all, can you tell me how are you going to apply this induction step to C?
So we have a circuit with one more gate, right?
Right,
So that gate can be either and or. So we can look at the two cases separately, I think.
right. So the way to do it is look at C, look at its topmost gate,
Yes.
look at both of the children. Okay, both of those children are circuits with smaller sizes, right?
Yes, yes.
So by induction, you can say that both of those functions are monotone.
Right.
Yeah. So there are two cases. Okay, let me write it. Uh, okay, yeah. So now what we want to prove? We want to prove that f of okay, yeah. So this is what we want to prove, right?
Right.
Yeah. Okay. So one way to do it is just like the straightforward way. Show that this function f satisfies the definition of a monotone function, right?
Right, right.
Yeah. Okay. So suppose We will show that. So this is all we need to do, right? Uh, for any x is equals to 1, so that f of x is 1, we need to show that f of y is 1, right?
Right. How are you going to go from f of x to f1 of x or f2 of x? Like something like that.
Oh, that's very simple, right? So f is or of f1 or and f2, right? F is f1 or f2.
Right.
So f of x being 1, what does that mean?
Either of them is one, at
Right.
least. Right.
Yes. So f of x equals 1 implies uh, f1 of x is 1 or f2 of x is 1, right?
Right.
Without loss of generality, let's say f of, okay. So now what can we do?
Since f1 of x is 1, f1 of y should also be 1.
Right. Because f1 is monotone,
And since f1 of y is 1, f of y is also 1.
right. And we are done, right?
Yes.
Yeah,
Similarly
so
for
here's the
and, in
case.
that case, both of them would be 1.
Yes, right. Yeah, so I'm not writing everything up to this point. I'm just going to write this part because everything before is the same, right? F is equal to F1 and uh, so F of x equals 1 implies F1 of x equals 1 and F2 of x equals 1, which implies F1 of y equals 1 and F2 of y equals 1, which in turn implies F of y is, yeah, so is this fine?
Yeah.
Yeah,
So like every argument given here is quite simple. Like
right.
I don't think if any sentence is there like I didn't know earlier or didn't like
Hmm.
understand, but for some reason like when you write it, it's clear entirely, and when I'm supposed to think for it, like can get lost in it. Like why doesn't it come to me?
Okay, so, okay, forget about the first question. At least for this question, you asked me this, right? F of x is 1. From
Right.
f of x, how am I going to go to f1 and f2?
Right.
Okay, so I think if you were the one writing this down, then while writing this down, you would have noted this, right?
Yes. Yes.
So, okay, maybe one thing you can try is if, like, try with pen and paper, right? If you're trying to do something.
Okay, yes. No, actually,
Yeah, because sometimes when you
what
write things down, you observe things that which you would normally neglect.
Yeah,
So
I
you
think I
know
went in the
every
wrong
statement,
direction because, like, when I asked this question, what I was actually thinking that X is a string, binary string, and I was
right?
thinking like some of the inputs would go to like F1 and some of the inputs would go to F2.
So that is true. That can happen. So it is completely possible that f1 only depends on x1 to xn over 2, and
Right,
f2 only depends on xn plus n over 2 plus 1 to xn, right?
right. So what I was thinking, but like in my mind was going like a partition of these bits, but that's not necessary. It may be that a
Right,
partition of the bits is actually what is happening, but they not be necessary. They may depend on entire like X itself.
right. So, but okay,
So
so
that
the way to get around that is the following. Uh, okay, suppose only a part of variables was going to C1, right?
right.
You can still think of C1 as a circuit over all variables. It is just not looking at the other variables, right?
Yes, yes, exactly. We can ignore the other
Right.
variables, right?
Yeah.
Yeah. So that came just after when you wrote like when you asked like
Okay.
what would be f1 of x.
Right. Because you don't know, like even okay, so one of the reasons I'm able to do this easily is because I've done this before, right?
That's one thing, right?
Yeah,
And you know what you're getting to, like you know the end in a way, like how to
right.
go through the proof, right?
Yeah. I mean, the way to sort of figure out what to try next. For example, over here, one of the things was okay, let's do induction, right?
Right.
I think that you can only develop if you solve enough problems.
Okay, yes, that's one thing.
Yeah,
Like if you solve, like if you do more proofs, you know how to like approach a proof
right.
better.
For example, like I have done similar proof with circuits and formulas for a very long time. So if I want to show that I'm combining something using a circuit and it gives me the desired result, for me, most of the time doing induction has worked. So I'll try induction over here again, right?
So you know like what set of tools you have to attack a certain problem.
Right. But the only way to figure that out is the hard way.
Do you do
Solving problem.
competitive programming or have you done competitive programming?
Yeah, I used to do it in my bachelor's and master's.
Okay, yeah. So like I do
Yeah.
it currently. I'm in my final year of bachelor's, so I
Right.
understand like that. During problem solvings, you can only use like
Yes.
tools you have, and with like more experience, only you get to know that what exactly to use.
Yeah. For example, when you initially start with competitive programming, it's very helpful if the problems are divided, right? This is a DP problem, this is a greedy problem, and so
Yes,
on.
yes, the tag helps, right?
Right. But
Yeah.
once you like practice a lot, you can figure that out on your own, right?
Yes, exactly. Like it's a with
Right.
a bit easier problems. You after just reading the statement, you get what you have to do, and then it's
Exactly.
just
Yes.
implementation, right? Yes.
Right.
Okay.
Similarly, like if you try a lot of proofs, you can figure things out like that. So, for example, if you see that you are supposed to do something, you are supposed to argue about the output of a circuit. One excellent way of like you would realize that one excellent way of doing that is like arguing about output of one git at output of every git one at a time.
All right. Right.
Yeah, which is
So
exactly induction, right?
yes. So,
Yeah,
like, I haven't gone through the exercises or if there are any in Sanjeev Arora, and like you mentioned in once, I think last
so those
semester.
so
Does it have good like problems to practice? Like, assume I'm a beginner in proofs and all.
for complexity theory, it has good problems,
Okay.
but not for circuit complexity.
Okay. Right.
So, in that book, circuit complexity is covered in just one chapter, and
Yes.
that's
Yes.
sort of in the advanced part of the book. So, what they do is they don't cover these like basic stuff like Karpachenko's theorem, Necheporov's theorem, this Skaya's theorem. What they do in that book is they cover some of the recent results.
Right. I've seen that
Yeah,
they mentioned the classes in the different classes which we haven't gone through in this course yet, like
right.
PY Poly and the other classes. I think
Yes,
I remember a few from the last semester.
right. P slash poly C0 and C0 TC0.
Yes. Yes.
Yeah.
So,
So I think once we get, so I think that would, I think he would, okay, after, okay, maybe this week or after this week, he'll start covering those classes, like constant circuit, constant depth overbound and things like that. So I
okay.
think then you can go and solve exercise in, from Sanjeev Arora.
Okay.
Yeah. Otherwise, I think sometimes he leaves some questions as exercises in the, okay, so here's one thing you can do. So sometimes in the lecture, he leaves some questions as exercises, right?
Yes. Yes.
And he doesn't always write every detail. And he also skips some cases, right? Saying that, okay, this is just similar, try it on your own, you should figure it out.
Okay, so like this week he just left one thing and it is like proving a part of the Valiance theorem. So since
Okay.
I don't understand it completely, I thought like I won't even touch it. So
Okay, a way to better understand Valiant theorem would be this. So it's one of the cases, right?
yes, yes,
So he solves a similar case and says you can use symmetry.
he
Are you clear
solved
about
one
that?
case and he said the other one is symmetric.
Right, exactly. So okay, wait. Symmetry is a little bit the issue. Okay,
Like
one thing you
it's
can try is like try to replicate every step he does, but with signs change, right? I think only the signs change, right?
yes, yes, I get that,
Right.
but like the problem is for me to do that, I must have at least an over like a bird's eye view of understanding of what is going throughout the proof, where we are going through with the proof. So
Okay,
that's what I
so
said initially. Like I understand each and every claim individually, but how that collectively is constructing the proof itself is a bit confusing to me.
okay, um, so this that you're talking about, this case is just in one claim, right?
And yes, it is the I think the first lemma
Right.
for
Yeah. So
the
whatever
proof.
what I'm
Yeah.
saying is, okay. So while you are trying to prove that case, you don't need anything. Okay, it's completely fine if you don't have a bird's eye view, if you don't know of what's happening outside that lemma, right?
No, it's the first one. All the claims used in are come as a part of proving this one itself.
Oh, right. Yes. Yeah.
So it is kind of top level. Just after the theorem, this is the first lemma, and all other claims are part of this.
Right. Okay.
Like
So
just proving this, like included so many things I've kind of forgot. Like mean value theorem came in. We are
yeah,
like
yeah, yeah.
differentiating things, and we have probabilistic arguments. So it kind of like all of those things went in once. So
Okay. So one thing I can try is the following. So in the next class, I can sort of okay, I won't go into the proofs of the claims, but what I can do you is the following. I can like try to intuitively tell you what each claim is trying to say and how it fits in the larger picture.
yes, yes. Like at
Just the
least
claim statements. We won't go into the proofs at all.
yes, it's just the statement
Right.
what they are trying to compute and what the bound show actually. Like what
Okay.
does it mean, right? Yes.
Okay, let's do it in the next class because if I try to do it in this class, I'll only like okay, so I haven't thought about what it everything is doing intuitively.
It might take necessarily more time than it's required. If you go through it once yourself, then it would be easier to
Right.
like make me walk
So
through it. Yeah, we'll
if
do
I
it.
right, so if I figure out myself what everything is saying,
Yes, yes, exactly.
intuitively it would be much easier for me.
Yeah.
Right.
I
Yeah.
think we should take it in the next one.
Yeah, but just remind me at the beginning of the next class. Yeah.
Okay. Yes.
Actually, that's a better way. Yeah. So now I want to. Okay, yeah. Okay, for week three, let's just do these two questions. I have one more question, but I think it's fine if we do it when we encounter multiple functions again. Okay.
Yes, yes.
So the reason I did it right now is because like when we encounter multiple functions again, there will also be some other things. It would be better if we focus on them and just remember these two. Yeah. Okay. So then, okay, let's look at week two's assignment. Most of the questions are recall, so we should be able to solve them quickly. Okay. So let's look at the first one. Two n-bit strings, sigma and tau, are said to be neighbors if and only if uh, there is exactly one bit position where they vary. Sigma and tau vary only in the last bit. They vary in all bit positions, and sigma and tau vary only the first bit position. So which of these is correct?
There is exactly one bit position for the
Right.
segment of
Yeah. So most of these are just recalls. So yeah. The second one is let f be a Boolean function from 0, comma 1 to tn to 0, comma 1. And let A be a subset of F inverse 0, B be a subset of F inverse 1, and NAB be the set of all tuples sigma comma tau, sigma in A, tau in B, so that sigma and tau are neighbors. And by Kharchenko's theorem, the L star size of F in the De Morgan's basis is lower bounded by what? And AB and AB square over size of A, size of B, the reciprocal of this, or size of A times size of B over NAB. So, which of these is true?
the second option.
Yeah. The third one is what is the best lower bound for the L star size of the majority function on n bits in De Morgan's basis that we can get from Kharchenko's theorem? n square over 2, n square over 3, or n square over 4?
I think it's for n square over 4, I think.
Yeah.
Like,
I mean, it's fine if you don't remember the exact constant we
yeah,
can
I
remember.
have the intuition because like only half of the bits we can flip
Right.
for
Yeah.
it to go to the other, right? Yes.
Yeah. So what I was saying is, with lower bounds, it's fine if you don't remember the exact constants, as long as you remember the order.
But for Kravchenko, the exact lower bound is important, kind like numerator is n square in most of the cases.
Okay. So I
So
think
if
you
I
can
don't,
come up with functions where, okay, so okay, there is a reason for that, right? The best Kharchenko can give is n square.
right, right. No, no, I'm
And
saying like when we are discussing Kravchenko only, we need the lower bound because generally it's n square. We try to find functions which have n square lower bound, but
right.
we have something in denominator. So,
So yeah, so okay, so you are right. When you have to solve these questions, when you have to answer questions like these, denominator is important. But what I was trying to say is, okay, so let's say after the end of this course,
like,
it's perfectly fine if you don't remember all these constants, as long as you know that there are some techniques
like,
which are very combinatorial and the proofs are very simple, and they give you order and square bound for some functions.
yes, yes, yeah.
Right. So it's okay to just remember these things.
Okay.
Yeah. Yeah. So the next one is the same question but for parity. So the lower bound on L star size of parity on n bits in De Morgan's basis from Kharchenko's theorem, n square over 2, n square over 3, or n square over 4. Yeah. So which
I
one's
think
true
this
over
is
here?
n square.
Yeah, this is n square. So this one would require some work. Yeah.
Yeah, this one I think is a good question. This is the one I was asking you a week or two before, like
Oh, last week, but that was a different question, right?
a
So
bit
what I
different.
had
Yes,
was,
once I looked at it again, it is a bit different.
yeah,
Yes, I think I got a generalization for this problem. So I don't think if it exists, like like it says divisibility by 7, but for any value like divisibility by any number, I think have a standard result. I think the way I showed it.
okay, so what's the lower bound?
Uh, the lower one, just give me a moment.
Yeah.
It is like the denominator is the value minus 1.
Oh, that won't work for every value, right? For
It should
example,
not be like something of the format 2 raised to the power.
right, exactly.
Other
Yeah.
than that, for all,
Other than that, I
because for
think
that it's just
it
kind of constant or
would
logarithmic. I think
work. Yeah.
I wrote it somewhere. Just a moment.
The only thing yeah, I
Yeah,
think it would
it's
work.
n square upon you can say like it like the number 7. Let's say it's the divider is d, so n square upon d
Right.
minus 1.
Okay. So the only thing I'm worried about, so 7 is closer to, okay, 7 is less than okay. The closest power of 2, 7 is larger than it, right?
Right.
I think this would work when that happens. What if the closest power is less than 8? It might also work, but I don't immediately say.
No, if I tell you the set C and B, then
Oh yeah, okay, so I know what the sets would be, but uh,
I followed your like explanation. You said the number of ones, like you proved number of ones
yeah, yeah,
divisible by something, right? With similar argument, like
right. So
I wrote it
yeah,
like
again, the sets would be similar, but what I'm saying is I'm not able to see that you will get it. Okay, so let me please see. B is 0, and why should everything else? Oh, it's just a power of 2, and whether you add or so it's add or we just again also try just look at add. And so starting with any number, okay, so what if it's something like 6? So if I add, so it's 2, it's 4, and 6, so this is 6.
are you
Okay,
trying like flipping the plates and saying what the mod value would be?
yeah, yeah, yeah.
That's quite confusing. I tried to do that for a time and I found out that I need to find the length of the mod cycle. Like after some time, the mod
Yeah,
values
yeah,
repeat.
yeah. So that's what I'm worried about. So when the number is prime,
There is another way I did this, like not that.
okay, so what happens is when the number is prime, the cycles would repeat. And the cycles would be like
I
would
think
sort of cover the okay, so
in
it's
any
seven
case,
over
the
here,
numbers
right?
would repeat, I think.
Yeah, the numbers would repeat, sure. But what I'm worried about is would they cover, so let's say this number was k. Okay.
Right.
So what is happening in the case of 7 is uh, when I add powers of 2, I get half of the numbers. When I half of the numbers in 1 to 6. When I subtract powers of 2, I get half of the numbers in 1 to 6.
Right.
Okay. This I am sure would happen when this is prime.
Okay.
What I'm trying to think is, would that also happen when this is not prime, in particular when this is a multiple of 2? For example, let's say
Uh,
6.
no, no. I tried it manually and for some cases it doesn't cover all the mod values.
Wait, so does it only work when this is prime?
Okay, your audio got stuck.
Wait,
I'll
no, no,
tell
no,
you
no.
what I tried.
Okay, no, no, no. I think it would
Oh,
work every
your
time
screen is
this
frozen. Am
number
I
is,
audible?
yeah, you're audible. Hello? Hello? Can you hear me?
Yes, yes, I can hear
Yeah.
you now. What were you saying?
So I think it would work whenever this is odd.
Your audio again went out.
Oh, okay. So what I was saying is, it would, let's say this 7 was k, okay.
Okay.
I think this n square over k minus 1 would work when k is odd.
I say n square over k minus 1 would work when k is not like of the form 2 raised to the power something. Other than that, it would work.
Okay, so I see why it would work for odd. Okay, let me quickly see why it could work for even as well.
Okay, so let me just reverse it this time. You try and I'll try to give my answer and you'll check
Okay.
whether like my answer is right or not.
Okay, so okay, I don't okay, so okay, so I can tell you what I'm thinking. I'm not sure
But,
that's what
I'm,
you might know about it. Okay, so whenever this number is odd,
okay.
2 is a generator of GK, the group GK.
I remember these words, but I don't remember their definition.
Yeah.
GK. Okay. So
So
just
basically,
give me a moment. I will get it.
yeah.
So you're saying like using
Okay, that's a
exponents of
better
2, I
thing.
can.
Okay, let's forget about 7.
Okay.
Let me do the proof that I have for general case and see what case it works for.
Okay. Okay.
Yeah. Because I think we are doing the entire proof for an arbitrary case, then I would write it down for 7. That would take twice the time. So let's just do it for general case.
Oh, we have to discuss weekend also. So should we just like cover this question and discuss this at the end, or should we like take it at the moment?
Okay, so I think we can do it now.
Okay.
Because
Okay.
I think
Yeah.
someone else also emailed me that I should solve this question.
Okay. Okay.
And
Okay.
what we can do is, okay, so the good thing about week one assignment is, okay, some of them are recall questions
Right.
that I can just mark the answers and upload the notes, and that should be fine. There are some other questions where you have to solve things, but a lot of those, okay, okay, so at least two of those I would also need as corollaries in so as like claims in the next session for
Okay.
week
Okay.
three when I try to solve week three's assignment. So I can cover them there at that time. Or we can also like in the next session we can also look at uh, week one's assignment completely. So next session what we can do is week one assignment and week three assignment. And the reason I'm saying that is because in the next week I think he's covering adders and subtractors and those circuits, right?
Yes. Yes.
I'm not sure there are too many questions that you can solve about them.
Okay. So
Yeah,
that's
so
week 4, like next to next session.
yes.
Okay.
No, okay, so this is
Okay.
week three
Let's.
session.
Yes, but we are
Yeah, so
not
this is week three session. Next
in week
time we do
3.
week four session. By that time, week three's assignment deadline would have passed. So we can cover
Yes. Yes. Yes.
some
Okay.
questions from week four, then week three assignment, and then week one assignment.
Your audio is breaking.
Oh, okay. So,
Yeah.
so by the time of the next session, week three assignment deadline would have passed. So what we
Yes, yes.
can do is cover some questions from week four, like what, two, three questions,
Right.
then move on to week three assignment and then week one assignment in any order. Yeah,
Okay, okay.
yeah.
Yeah.
Because like in week one, for example, there is this question, right? What's the smallest formula for XOR?
It's in week 4 or week 3? I don't remember. Actually, in week
In
1.
week one's assignment.
Okay, I don't remember.
Oh, let me think it was there.
Smallest formula.
Yeah, this one. Pick the smallest upper bound on the demoted form of parity.
Okay, okay.
Yeah, I think
Right.
this will also need in week three and week four.
Okay.
Yeah, so I'll just solve it at that time. Yeah. Basically, we can take week one next week. It should be fine. Yeah. Okay, so yeah, so what we'll do is we'll do this for general key, right? Okay, so let me first mark the answer. It's this. Okay, so let A be. Okay, let me define B first. The set of all. Okay, yeah. What? B is just F inverse one, and let P be this, and A be F inverse zero. So these work for seven. Are these the same A's and B's in your proof for general K?
Uh, yes, yes.
Yeah. Okay, so okay, then let me just keep these A and B, and let okay for all I in K minus one, let AI be X such that X1 to Xn is congruent to I mod 7, sorry, mod K. Yeah. So this notation just means numbers from 1 to K minus 1. So what we have done is we have taken all strings and divided them up into K parts, right? The first part is B, the rest parts are AI.
Right, right.
Yeah. So we are dividing based on the modulo, right?
Right, right.
Yeah. So these are not equivalence classes. Okay, fine. Okay, so now what's the size of B? 2 to the n over K. So this would be a ceiling because you have to start counting from zero, right?
Right, right.
Yeah, so for example, for 7, let's say n was 3, then for 7, if you looked at floor, it would be 1, but if you look at ceiling, it's 2. Then I need two things, right? A 0 and 7. The first and last one.
Uh,
Yeah, so
yes.
yeah, so okay, are you convinced that size of B is floor ceiling of 2n over k?
Ceiling of 2n over k depends on the choice of k, right?
Okay, so let k be anything. Uh,
Let's try some value of n and k.
okay, yeah, so I tried 7 for this. This works for 7, but I think it would be better if we do it for general k. So let k be anything, right?
Okay.
0 would be in B.
Yes, yes.
Then, okay, yes. Then k would be in B, 2k would be in B, 3k would be in B, and so on.
Right.
So nk would be in B, where,
And k would be less or equals to 2 raised to the power n.
right. Okay, this is sort of, yeah, now B would
K
because it
is
is a
less
number
than
and this
equals to
is right.
2 n.
So this is less than equals to 2 to the n, right?
Yes, yes. I think
Okay,
m and k replaced would be a better result. I think we are trying to find the size of the set, right?
right, yeah.
Yeah, I did also the same thing.
So m would is less than equal to this implies m is the floor of this, right?
Right, right.
Okay, so it's supposed to be, it's not this, it's supposed to be floor plus one.
Yeah. You can also think of it like this, like if 2 raised to the power n is just next to the multiple of k. So if you're taking the ceiling, you are also including the next multiple, like, in a way.
No, no, no. Okay, so if
Yeah,
that's
the result follows. Yes.
right, no, so okay, so this one is better. So okay, so earlier I had a ceiling of 2 to the n over k, right?
Right.
That is undercounting because what can happen is 2k might divide 2 to the n. It won't happen in our case because we are assuming k is odd. Sorry,
Right.
k is not a multiple of 2. Sorry, k is not a power of 2,
Yes. Yes.
right? But the right thing would be this, right? Floor
Right.
plus
Right.
1 because it's m plus 1. We are not looking at 0 over here.
Yes. Yes.
Yeah, so it's floor plus 1. But for our case, it's just the ceiling. Yeah. Yeah. Okay. So now we are okay. So now what I'm going to do is I'm going to look at the size of NAB in the terms of B, right? So NAB terms. Okay. Uh, fix uh, X in B. Uh, okay. So strings in NAB are just going to be neighbors of. Okay. All strings in NAB. Okay. NAB is a tuple of the form sigma comma tau, right? Let me just call it X comma Y. Okay. Okay. So NAB is a set of tuples of the form y comma x, where y is in A and x is in B, right? And x and
Yes.
y are neighbors of each other. Okay, let me do it like this. So this is the question we are trying to answer, right? So first of all, x and y are going to be neighbors. So x is obtained from y by flipping some bit, right? Okay, so now there are two cases. Hmm, okay, so this is the first case. Okay. The other case would be when you flip a 1 to a 0. And the reason I'm doing this is the following. So when you flip a 0 to a 1, you're adding a power of 2, right? Hello?
Yes. Yes.
Yeah.
Yeah.
So x is equal to y plus 2 to the, okay, I've used too many i's, use j. I think n minus 1. Yeah. Okay. So And okay, what I want to say is, okay, so the number of, for any y, we are trying to count the number of x comma y in any b, right? First, we are looking at all the x's which are obtained by flipping a 0 to a 1. And so the number of such x comma y tuples would be uh, number of ones in y, right? Sorry, number
No,
of
it's
zeros
not
in y.
necessary. I don't think it would work.
Right?
Like because you can't get an x by flipping any zero.
Oh, right. Okay. It's the okay. Yeah.
You
If
could,
k is even, things can go wrong.
yeah, you can only get for some specific multiples of 2 to the power something. For example, if you get by the bit value 1, then you can get the same with bit value 8. I mean, the bit representing the value 8. And for
Oh no, no. Okay,
in
that's
case of
fine.
7, I'm saying,
Right.
right?
So what's going to happen is uh, when you flip the okay. So for bit value one, you would get x comma y, where x lies in a0. Sorry, a1. Similarly, so basically x mod 7 would be 1. Similarly, for the bit value 8, x mod 7 is still going to be 1, but these two are different x's, right?
Yes, but they are still in the same set.
Right, so they are in the same set, but what we are trying to find is how many neighbors of B lie in A, right?
No,
So
you're
as
trying to
long
find
as
how
there are
many
two,
neighbors of A lie in B. You have fixed a Y and then you're trying to obtain an X, right?
yeah. So, okay, so I fixed a Y is in B, and I'm trying to find how many neighbors of Y are in A.
Okay,
So the
I think
reason,
the representation is a bit opposite in this case. Uh, we have like B which goes maps to 1 and A which maps to 0.
okay, that's the issue with the questions. So when
No,
is
no,
one, when is the output? What I'm saying is when is the output one?
right,
Output is one when x1 to x is divisible by 7.
right,
So when I say f inverse 1,
right, right.
I have, yeah, so it would have been much
So,
better if this
yes,
were 0 and this were 1.
no, no, that's all right. I think you have taken Y belongs to B.
Yeah, okay, so y belongs to B. So what I'm trying to do is,
No, no.
I have a
The
string.
problem is like I'm taking the tuple as the first argument from A and second from B.
Yeah,
So
so I
if
have done the
we
same thing,
reverse
right?
that,
It's x comma y, a comma b.
okay, okay, yeah, it's all right. Okay.
Right.
I got confused with
Yes,
that,
that
but
okay.
yeah,
So
still, what I'm
initially I had
saying.
x over here. That's why I changed it to y.
Okay, yes, yes, that's
Yeah.
fine. But still, what I'm saying is that you cannot get such tuples for flipping any zero to a one.
Why?
Uh, okay, just give
Okay,
me.
so okay, okay, let me prove this.
No, 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 no. Your uh, x is in which set? X is in y is divisible by t. So y is a string which is divisible by k, right?
Right.
And you are flipping any bit of it, so it must be in. Yeah, yeah. This direction is fine. Yes.
Okay. Yeah.
Yeah.
So we claim that x is
The,
in
the,
A.
the, the, the symbol I thought that y is not divisible by. You are taking
Okay.
trying to make it divisible. Yeah. But this entire argument is only in the case when k is not divisible by two, not a multi and not a power of two.
Yeah, because if it's a power of two, the circuit is very simple, right? Just look at the last few bits.
Right?
Yeah. So over there we can't hope to get a lower bound.
So the size would be constant, right?
No, the size would be order n because like arbitrary final. So
Arbitrary.
let
No, but since k is fixed, uh, we know the number of bits to look at.
right, but okay, but k can be order like k can be n over two, right? So the size grows with k.
Okay.
Okay, so basically, if it were, okay, if k were 2 to the I, then you would have to look at the last I bits.
Right, right.
But I itself can be n over 2, so you would have to look at n over 2 bits. So
And
it's not
no,
a constant, it's it's like log k. Size would be log k.
yes, yes, size would be log k. Yeah, fine.
Yeah,
Right, right. Exactly log k.
right. Yeah. Yeah, because yeah, it's power of p.
Right,
Yeah, so number of such x comma y is the number of ones in y, right?
right, right.
Okay, and case 2 would be,
Well, it's the same argument if I'm flipping a 1 to a 0.
right. So x would be y minus 2 to the p for some p and okay, and again, yeah, so again, this would be in A, right? Because k is not a power of 2.
Right, right.
Yeah, okay, right. So, yeah, okay, it's fine. Yeah. Okay, so over here it should be zeros. So, yeah, so we get this, right? Is this fine?
Yes, yes. Yeah.
So now, what's this? What the fuck is this? Okay, and this is going to be size of b n square size b square over so this is uh, n square times size of b, okay, minus 1, right? So I cancelled out 1 over here and I took this in the denominator. Is this fine?
Yes, yes.
Yeah. Okay, so now we want to lower bound this. So we want to upper bound the denominator. So we want to lower bound size of p, right? And we know that size of p is ceiling of 2 to the n over k. So the lower bound would be just 2 to the n over k. So this would be n square over k minus 1. Yeah, so is this fine?
Yeah, yeah.
Yeah, so okay, but look at the question. The question is asking us what is the best you can get, right? All we have shown is that n square over k minus 1 is possible. But we also need to argue that something better is not possible, right?
It says, acha, okay. No, so we have to choose the best from these options. So that we can
Right.
get, right? K minus 1 is possible. I think the better argument would be possible when we look at the, like by flipping a bit, what different mod values we can get.
Exactly.
Right?
Yeah, so that's what I was worried about.
Yeah, so I was
Yeah.
worried about that for a week, I think, and I asked also you
Okay.
for hint. And what I
Oh,
found
okay.
out, like this worked in the end, and that's the same result, that same thing I have done, right? And in fact, I think this would work for
Oh,
most of the
let me.
problems where we can like single out the set and which belongs to f of one, like f inverse one, and we can put the rest of them in f inverse zero.
Okay, right,
So,
right. So,
right.
uh,
So
no, but the
this,
issue over here is the following.
like,
So, over here, I have picked A to be f inverse 0, right?
right,
But, okay, so, okay, choice of B is pretty straightforward, right?
right, right.
What I need to show is there is nothing in f in, there is nothing in A which is redundant. So, suppose
Yes, yes,
I
yes,
could
yes.
come up with a better
Okay.
A, right? So, what I
Right,
need
right,
to
right.
show is, okay, my B is pretty straightforward. Let's assume that. Let's
Yes,
assume that this is the best choice of B. Okay. What I need to show is every element in A is a neighbor of something in B.
exactly. So,
Right.
y- the but there's a problem that we need to like. It might be possible for some of the case, but it like would be difficult for some other case. But the reason I'm saying this, like by flipping a bit, we are exactly adding or removing a power of two.
Hmm.
So it's either we are adding 1, 2, 4, 8, 16, or something. And if we look at k minus k, exactly k of those, after that it must repeat,
Yes.
right? So it may repeat earlier, right? In case of 7, it is exactly 3 of the
Yeah,
bits,
so
right?
that's what I was worried about. Repeating
Yeah,
earlier. So
yeah,
that would happen when so the number you pick. So okay, so what you're doing is you're looking at powers of two, right?
right.
So if two were not a generator of the group,
Okay.
then you it would repeat early. So okay, what I can
So
do is okay, I can explain it over here.
you you mean like there is a standard result for this, like the size of the cycle of remainders?
Yeah, yeah, yeah. I can sort of I think I can do it. Okay, if
Yeah, I
not
was
the
looking
size,
for it.
if not the size, I can at least show. Okay, I can at least show something. Let me
Okay.
try. Okay.
Yeah.
So to show that n square over k minus 1 is the best lower bound that we can get.
Yeah, because I tried to find it, and like results regarding these subjects rarely like are found in Google or some forums like Stack Exchange or similar. So I
Yeah.
tried to find the series in OEIS. I think you know about OEIS, Open Encyclopedia for
Oh
Sequence.
yeah, yeah. Okay.
Yeah, it is
Okay.
a sequence. Yeah. So
Yeah,
I
yeah.
thought maybe I get a formula there, but nah.
Yeah, but I mean, okay. So you were looking at it. You were looking at it from in the wrong place, right? You were looking at it.
Right.
Okay. You were trying to find for something in complexity theory, right? It's actually a group theory. This.
Okay, yes. Since you
Yeah.
mentioned generators, right? It's
Right.
part of that, right?
Group theory or number theory? Yeah. Because I mean, this is so simple. You can do it using number theory as well.
Yeah, but we shouldn't like exclusively separate these topics, because like we use tools from one in the other repeatedly.
Yeah. The only problem is you need to realize that you have to use that tool.
Yeah, I
That's very
can't do
difficult.
that, but you
Yeah.
can. So that's the difference.
I mean, okay, I can only do this over here because, okay, so I tried the proof for 7 and I
Right,
noticed something. And
right,
I've
right.
seen things that I did before, so I knew, okay, This has to do something with
So
generators.
you arrived because you understood generator functions that way, right? Like you knew some kind of results about like that
Right.
Q is a generator of the class. Even I knew the definitions about that. If I knew that what is a
Oh,
generator
but
and
okay,
all.
not only do I know it, I've used something like things like this like before.
Yeah, yeah. Okay.
Yeah.
So it's again experience. So
Yeah.
the arguments come back there.
I mean, yeah, I mean, okay. I think there is a quote by Euclid. Okay, so Euclid was once teaching geometry to
Okay.
a prince or a king. Okay,
Okay.
and that person was like, okay, doing it the normal way, solving the problems is too hard. It is too much work. Is there a shortcut? And Euclid was like, sire, there is no royal road to geometry. So it's the same thing for math. You have to practice. Yeah.
So the lecture for circuit complexity just turned philosophical.
Yeah. Okay, so to show that m square over k minus 1 is the best compound it can get, yeah. Uh, for all x in A, there exists y in B such that x comma y in any B, right? Because this shows you that nothing in A is redundant. So in particular, you couldn't have come up with a better expression over, better size over here, right?
Yes, yes.
Yeah. So for example, if I'd been able to do something like over two over here, then I would have gotten like two over here, right? Better
Right.
than. Yeah.
So in
Okay.
this case, for
So
7, it would be like fine.
right.
You
Yeah.
can
Okay.
show that.
So uh, y is
So are
equal
you
to
going to show
0.
for 7? Like we don't have a smaller.
Okay. So I'll try it for arbitrary k. If I don't get it, I'll drop down to 7 and then I'll try to generalize. Okay.
Okay, okay.
Okay. So we know that y is equal congruent to 0 mod 7, 0 mod k. And okay. No, wait. Um, okay. No, no, no. Okay, yeah, okay. So let me change this statement. So over here, every time we should show that for all x in A, there exists y in B, right? You know, let me change the statement such that for all y in B, there exists. Okay, so my claim is if for all y in B, yeah, if for all y in B, we show that there exists x in AI, so that x comma y is in NAB, then all AIs are required, right? Okay, no, this is not satisfying.
No, like for B, we have already showed this, right? For each Y, the
Oh, no,
corresponding X
each,
exists.
yeah, in A. So now I'm saying in each AI.
Okay, we need to show for each X there exists the corresponding Y in B.
So okay,
We need,
if you show that, then also you could argue that all of A was required.
right.
I am trying. Okay, so this statement is easier to prove. So what I'm trying to do is argue that even if you prove this, then you can show that all of A is required.
Okay, one thing they like about the whole like best possible bound, we are
Right.
assuming that we need the entire like F inverse one, right?
Yes,
But if
that we
we
are
look
assuming.
at the proof we
Yeah.
did for majority, I think so that also was like we didn't like pick the entire F inverse as set B.
Yes. Yeah.
So it might be possible we may be getting a better result by picking only some of the x's which are no, sorry, some of the y's which are divisible by k as part of set B.
Okay, that won't happen because regardless of what you have in B,
Right.
okay. So suppose I were to prove this.
No, the reason I'm saying that because if we target y's, Like if we choose wise in a better way, it might be possible that we may be able to construct an A such that A is not A doesn't have any redundancy. What I'm trying to say is that,
Okay.
right?
Okay.
So
So pick any B. Okay, pick any B you want, right?
okay,
Suppose you show that for every okay. Okay. So suppose I show this, then okay, no, no, no. So basically, what I'm trying to do is pick any Y you want in F inverse zero.
right,
If I show that all its neighbors are in each of the AIs,
right.
then the only way I'm going to get n square over here, uh, and n square not something like n square over 2 or something like that, is if I pick all AIs in my A, right?
Okay, so you're saying that if we take a subset of B, we might not get exactly n as the number of
No,
neighbors
no,
for
no.
a
So
particular
what
string.
I'm trying to show is if you take a subset of F inverse 0 as A, you might not get the best. B doesn't matter because regardless of what you take as B, you're going, as long as you take the entire A, you're going to get n squared times size of B square over size of
No,
B, right?
but I'm saying like if we pick a subset of B specifically, we might be able to construct an A says a subset of A again, which is like uh, which doesn't have any redundant strings, which doesn't have any redundant strings. Like the reason I'm saying this for seven specifically, I tried and I found out that there are no strings which have a single one or a double one, like two ones in the string, and they are divisible by seven. But with three ones in the string, the obviously seven itself has three ones, so it would
Okay,
be divisible. So I thought like maybe if we approach it in this way, we might get such a set.
okay. So
So you get
what
the
we're
idea
going to
what I'm trying to say actually.
yeah, yeah, okay. So if you pick a subset of B, okay, so what I'm trying to say is as pick any B you want, the best you are going to get in the numerator is n square times size of B square, right?
Right, right.
And over here the best you are over here size of B would be there, right?
Yeah, yeah.
So okay, this is just the same as and this gives me this, right? So over here, if I had picked a smaller B, I would have gotten a better bound, right?
Yes, if you pick a smaller b, you could also pick like a smaller a, and they do not need to like cover the entire 2 raised to power n strings, right?
Okay.
In this case, we are getting exactly a partition, right? The
Wait,
approach
wait,
you have
wait, wait,
used
wait.
above.
If I had picked a smaller, the two, okay, so over here I'm picking something that's size 2 to the n over k. If I had picked something of size 2 to the n over k over 2, I would have connected something better, right? So yes, a smaller b. Yeah. Wait, can I come up with a smaller b?
Like we are looking at the ratio b over a, right? Size of b over size of a.
No, no, no. Okay, so we are looking at just this ratio. Okay, so A is completely dependent on B, so we don't need to worry about A. All we need to worry about is size of B relative to 2 to the n, right?
No, I'd say that we need to worry about the size of a,
Why?
because like the above construction assumes like a is complement of b, like everything not in b
Oh,
is a
okay.
part of a. I'm saying that we do not need to
Oh,
pay.
your voice
Yeah,
broke.
yeah,
Okay.
it got muted. So I'm saying like we do not need to pick everything not part of b as part of a. We can leave out some things there also.
Okay. So what you're saying is pick a smaller B,
Right.
and that would was okay. So that would give you this.
I mean, you can rewrite n square. This has n square size of b
The
upon
size of B.
size
One
of
second
a,
here. Okay, okay.
right?
Can you repeat that?
Yes, exactly this much, right? N square
Okay,
is
right.
n square remains there. We need to like minimize the ratio b over a.
Okay.
Yes. So one way, like if we partition this, right? So if so b is fixed, and we need to reduce a as much as we can do. No, we need to show that there is
No,
no redundancy.
once you fix B,
Right.
A is sort of fixed. Okay, the best A is fixed.
No, if I fix b, the best a I have is the complement of b.
No, 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 no. Okay, that is only true if, okay, so let's say B is a strict subset of F inverse 1. In complement of A, complement doesn't make sense, right? Because then A would start having strings in F inverse 1, which is not allowed.
No, by complement, I'm saying that the ones that
All its
have to zero.
neighbors?
No, no, no. The words might seem wrong. Like,
Okay.
uh, uh, sorry. So in the above construction or construction till now, we have picked
Hmm.
a set B, and all the remaining strings that are not in B, we have put them as part of A, right?
Okay.
And this is the best, given that we show that none of the strings in A are redundant,
Okay.
right? So that's one of the thing, right? But suppose if I like have the set B as subset of something of f inverse 1, right?
Okay.
And A as something as subset of f inverse of 0.
Right.
With this, I think we may get a better like a result, because like we have freedom of choosing the set B and A based on the construction.
Hello. Your voice broke again.
Am I still audible?
Yeah.
Yeah. So in the above construction, if you fix B, you have a fixed A. But
Hmm.
if I pick a subset of B, I am free to like constructing a subset of A, and we may get a like smaller result. And that depends on the construction. What I'm trying to say.
Right. Okay. So what I'm trying to do over here is sort of similar. I've picked any Y
Okay.
and I'm going trying to show that corresponding to that Y. Okay. So I want N. Okay. I want NAB to be N times size of B, right?
Right. Right.
So what I'm going to show is uh,
Okay.
I couldn't. There exists an X in every AI.
Yes, yes, I think I get the problem with my argument. Like, I'll tell you the sets A and subset of set B and A I have had in mind, right?
Okay.
So I think it would make it a bit more clear. I said a moment ago, like if I have 3 bits, it might be a multiple of 7. Like it is
Oh,
possible,
so
but
N
with
is 3 over here.
at least three, one or two,
Okay.
and 0 bits is not a multiple of 7. It's clear.
Okay.
Okay, so let's pick all the such strings which have exactly 3 bits in them, and they are a multiple of 7, right?
Okay.
I am picking such strings,
Wait, why are the multiples of 7? Because, okay, yeah, fine.
right? है
Yeah.
And in this case, if I like flip any of the ones, I would get a string which would correspond in A.
Right. Yes.
Well, if had the original bills B, it would still work. So for a subset of B, it would still work, right? So in this case, like B would be a set of strings with exactly 3 bits, and it is a divisible as n. A would have like exactly 2 bits, right?
Exactly 2 or exactly 4? Because you can flip
Exactly
zeros to 1.
two, because I'm. It can
Oh, so,
have 2 and 4 if I flip 1 to 0 and 0 to 1.
right. So A would be like exactly 2 bits or exactly 4 bits. It's union of these two, right?
Yes, yes, exactly two
Right.
bits or exactly 4 bits, right? So I see the issue with this, like the in numerator we won't get exactly n square,
Right.
right? But we have sets which are, I think, don't which are not redundant, almost not redundant. It,
Yes. Yeah.
mathematically, but I'm saying this ratio of size of B over size of A would be a better result. But I think the compensate by compensation we are like having an extra factor
In
n
N.
square, I think.
Right. Right. Yes.
Yes, I think there my argument falls.
Yeah.
So like
Okay,
this
so
was my idea for getting a subset of B and A, but I like we might
hmm,
also get like not every string is a name, right? Okay. No, it's still like if I have a string in B, like such created B, flipping any bit would have a neighbor in A, right?
yeah, so okay, so
The n square remains.
wait, okay, so if you are just yeah, okay, okay, answer remains. Yeah, that's true.
But figuring out the size of A would be complex, I think.
Okay, I think no, 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 it won't be complex. It's just n times size of p. Oh no, wait, yeah, redundancy again.
And figuring out a size of B would also be complex, I think.
Yeah, okay.
So, okay,
Fix any
okay.
y.
We need exactly 3 bits, but such a number should be divisible by 7.
Yeah, okay, so fix any y. Uh, F and B is going to come with
Oh no, B would be simple, I think. Uh, if a number is divisible by 7 and there are exactly 3 bits, one bit should correspond to like one, the mod value should be 1, other bit should have mod value 2, and a third bit should have mod value 4. So
yes,
for
yeah.
the n bits, from starting from least significant bit, we can group them by 3, and like what I'm trying to say, 1 8 sorry 1 8 64 and so on. I exactly one of them should be 1, 2
Oh, right,
16,
yes.
and that exactly one of them, and similarly for 4
Yeah,
and so on, right? So yeah, we would get B, but how would we get A, size of A?
yeah. I mean, over there you will have to over there. Yeah, you will have to use inclusion exclusion because there will be double counting, right?
Yes, like flipping one
Yeah,
of the 3 bits would get the same, would
yes.
get one string, and flipping other.
Okay, so okay, so this is just one construction. Suppose you pick any arbitrary b in F inverse one, it's going to come with its n many a's, right? N many corresponding x's.
Yes, yes.
And what you are trying to do is show that by picking a subset, there are too many redundancies. Yes, okay. Basically, what you're trying to do is this, right? You pick the subset of B,
Right.
and so all of them are going to give you every element in B is going to give you n times size of B many elements in A and A comma B. But the way to reduce size of A would be to argue that for many elements in B, you get the same element in A.
For many elements in B, we would get the same element in A.
Okay, so think, okay, consider this case. It won't happen, but consider this case. Suppose for every B, you get the same set of, okay, so for, let's say for every Y in B, you get the same X values, same NX values,
Every Y we get the same X.
same N many X values. You would get N many X values anyways.
Right,
Suppose
right.
all of them are the same. Then size
Okay.
of A would be much smaller because there are too many redundancies.
Right, right.
Yeah. Okay, so the question is there a way to come up with a construction of a set so that there are too many redundancies? So everyone is going to be doing that. And
But again, the problem remains, right? Because I am specifically picking a set B which has exactly 3 bits, right? In this case, right? So
right,
my specific construction may get me a good lower bound, may or may not. It may be
right.
better than n square over k minus 1. It may not be. But it again depends on what specific subset of B we are picking.
Yeah, so
And
that's what I'm trying to do. So what I was trying to do is just pick any Y
right?
in F inverse 1 to be in B, that would give you n many x's. Somehow, can you argue that these are pretty distinct?
I think the way you were initially going for proof, you would have to show one more thing, that removing a particular y from B and correspond the neighbors which correspond to this particular y only, like removing this y and the neighbors of this particular y
Mhm.
in A, removing both of them would not give you a better lower bound.
Okay, not okay. So not only would it not give you better lower bound, it might. Yes, okay. Okay, so if you were to do that, then like you would also lose some pairs of other y's, but that would be too complicated to argue.
No, no, I'm saying like those x's which are specifically only neighbors of this particular y, right?
Can such an x even exist? So okay, so that the issue is you are trying to
Oh,
remove one thing from y at a time, one thing from f inverse one at a time, right?
your audio.
Oh, so what you are trying to do is remove one thing from f inverse y at a time, right? So you are
Yes,
removing
kind
one
of.
string from f inverse y
Okay, okay, yes.
and not keeping it in B, right? I
Yeah.
don't think there would be any x in A which is not which is just a neighbor of this. But what would happen is when you remove a big chunk of P, this would happen. So if you just remove a very small parts of P,
So you're saying for one y this would not give any result,
this
but if I have more than one y's, we would have some values, right?
right.
So
So
I said
is
one y, but it could be any subset of the y's.
yeah. So, okay. So what you are proposing is like remove one Y, argue that you would
At
get better
least,
lower bound.
at
That
least would
would
be a
work.
better word, I think. At least one y.
Okay.
Yes.
Yeah.
Yeah. So basically, I think what you are trying to show that if you have taken the entire set B, right, and there is no redundancy in set A, we would get a lower bound, a good lower bound, right? Yeah.
Right.
But Kharchenko's theorem doesn't like ask us to take the entire set. We can take any such suitable set.
Yeah.
So again, the arguments come like if we are taking subsets, we should also not get a better lower bound. If you are talking about best,
Right. Okay. So okay. Right now I was just trying to do it for B.
okay,
Yeah. Okay. So okay. Yeah.
okay, we are over time, but still,
Yeah, okay, so this I can do very quickly. Yeah. So y is 0 mod k. So okay. Now what do I want? I want at least half of these. Okay, so if okay, if this, then what am I trying to do? So I'm trying to show that if okay, then for every y, I can solve this. Okay, so my claim is if 2 to the 0 mod k to the 1 mod k to the 2 square mod k and so on, this is equal to the set 0 to k minus 1. Then for every y would get elements from every AI. Okay,
Yes, yes.
okay. Why? Because okay, so when you are flipping zeros to one, you are adding powers of two. So you would get half of these many, half many AIs at that time. And when you are flipping zeros to one, sorry, when you are flipping ones to zero, you are subtracting powers of two. So at that time you would get the other half.
Yes, yes.
So basically, what you would be doing is two to the zero, to the one, to the two, and so on. And two to the minus one, to the minus two, to the minus three, and so on.
Yes. Wait.
Okay, sorry, minus two to the zero, minus two to the one, and so on. Yeah. Okay. So yeah, so basically, two should be a generator of zero to k minus one, which means okay. Let me write it in and explain. This one. Two should. Uh, oh, so zk cross is wait. Why is zk cross? Zero is also allowed, right? So this should be a. Wait, why should be? I think this should be a generator of this. Four. Oh, then it would be two, four, six. Oh yeah. Okay, I won't get zero over here, right? Because I'm adding powers of two, and two is not divisible.
Right.
But yeah, k does not divide power of two. Yeah. So yeah, it's zero is not there, so I can get zk cross. Okay.
So you're only considering when you are like flipping a 0 to 1 the case, right?
Okay, so when I'm flipping a zero to one,
Right.
I would add powers of two, right?
Hey, using the generator, we can only like increase the power. Like, can we do after that the
Okay, so you
other
can also
mod that
decrease it, right? So okay, so if you were to subtract two to the one, okay, so if you were to subtract a one to a, if you were to flip a one to a zero, you would be subtracting something, right?
it's basically k minus 2 to the something, right? And mod of that.
Okay, so y is zero mod k, so y is m times k, right?
Yes, yes.
So if I were to subtract two to the L from it, then this is m minus one. Is this what you were saying?
How is this m minus acha, m minus 1 times k minus 2 to the
Yeah. Okay, so this is just the additive inverse of 2 to the L. What is the multiplicative group? Okay, so when you add, okay, yeah, now I need, okay, yeah, there is no that simple way of doing this.
I think what I remember, like using a generator, you can like keep multiplying that and take modulo k. So that would like cover the cases we are like flipping a 0 to 1. But how
Okay,
like this case where like flipping 1 to 0, how to capture that? Like I don't know what like how generators cover those in this context.
okay, so when you, okay, at that time you're subtracting, so you would get something like this, right?
Right.
Okay, and what I want to argue is k minus 2 to the L. So k minus 2 to the L is an element of, right?
Minus 2 to L is an element.
Oh, wait, no. Okay, this is true when k is a prime number. Okay, so okay, no, no. Okay, so if okay, fine. So if two is a generator, then and this element is in the group, then you would get it, right?
Like if 2 is a generator, so it already generates like all the values till k minus 1, right?
Right?
So if it happens like by flipping some 0 to 1, it would also happen by flipping some 1 to 0.
Okay. Yeah, but for a different string, right?
Yes, for a different string, right? Yeah.
Right. Okay, so basically, okay, when you are looking at something mod k, you can also subtract using just using generators, right? Because when you overshoot k, it's subtraction. Okay.
No, we just like uh remove, like it's not subtraction exactly, like
Okay,
because
so if you are adding eight, okay, let's just look at seven. So if you're looking, if you are doing y plus uh, eight, that's the same as y plus one, right? So that's the same as y minus six mod seven,
it's same as y minus 6, right?
right?
No, it's same as
Y minus
y
six mod seven,
plus 7 minus 1, kind of like that way. But like you're finding the complements of each of the mods, right?
the additive
By
inversions,
complement I mean additive k minus
right?
that, right? So
Yes.
so uh, about but ho- but how, like using generators we could get those? Uh,
Okay. So what I was trying to say is minus six. Okay.
you if like if it's all right to you write the proof all once, then I think we should go over it again. Like just
Okay. Yeah. Okay. Okay. I can do that. Yeah.
yeah. So
So to and when does this happen? So yeah. So I okay. So I need k to be co-prime to two. So I need k to be odd. What goes wrong when it's even? Okay. So whatever. Okay. What I'm trying to do is this, right? So I'm starting with something which is equal to zero mod k. So far, okay. Right now, let me just flip zeros to ones. Okay. Then I'm adding uh, powers of two, right?
right, right.
Okay. And when I'm okay, so okay, fine. So I, and I suppose I get half of them. I want to claim that the other half you can get by subtracting. So it's okay. So suppose okay, so over here the issue is this, right? So what you are asking is how is minus two to the L? How can you obtain minus two to the L using two? Yeah, by just by using to the generator, right?
Yes, yes, exactly. Yeah.
Okay. Okay. So mod congruent mod k, right?
Right.
So if I can get k minus 2 to the L, By using 2 as a generator, I'm fine. Is that okay? Hello? Oh, I can't hear you. Can you hear me?
Yes, yes, sorry.
Yeah, okay. Yeah, so if I can get k minus 2 to the L by using power, by just using powers of 2, I'm fine, right?
Right, right. So,
But
like,
that
if
happens when 2, if 2 is generated, that would happen.
yes, yes, yeah, that would happen.
Right. Yeah. So basically, when you're going, look at like finite groups, you don't
After
need,
finite groups, the audio went.
oh, yeah. So when you're looking at finite groups, you can even get negative numbers, quote unquote negative numbers, by just like positive powers because of this cutoff.
Look, like if it's a generator, so yeah, it covers all of them.
Right. So basically, there are no negative numbers in finite groups.
No, once you take modulo, it's all in the range 0 to k minus 1.
Right. So like powers can also be covered by just positive powers.
So
Hello, is
even
this?
if like we don't think it about this much, like if 2 is a generator of the group like z star k,
Hmm.
so like even if we ignore the negative values, right, it covers everything in the range 0 to k minus 1, even though we only need 1 to k minus 1,
Right.
right. uh, but then we would need to argue like 2 is a generator of such a group.
Okay. Okay. So for Z star K, anything that's co-prime is the generator, I think.
Okay,
Yeah.
then it might also be possible that if 2 is not a generator, even in that case it might be like the case that it covers 1 to k minus 1.
Okay. So if 2 is not a generator, uh,
We need to show that it not should not
okay.
can
Okay.
only like,
Okay. If 2 is not a generator, it can't cover 1 to K minus 1, right?
yeah, if you show that, then this completes it, I think.
But wait, that's the definition of generator, right?
That is
Generator is something that covers the entire group.
okay, yes, right. So we don't need the entire group. No, we need only 1 to k minus 1.
Yes.
0 is irrelevant for me.
Right.
So that statement is only true when we also consider 0.
Which
Like
one?
that won't have any effect. No, for generators.
Oh, no, no. Okay. The group is this, right? The group does not have zero. So what I'm saying is,
Oh, so
right. Yeah.
yeah, the group itself doesn't have 0. Okay.
Yeah.
So you said like 2 should be co-prime.
Yeah. Okay. So I
Then
also
only
need to
this
come up
is
with a counter example. That shouldn't be difficult. So let's say 6. So I get 2 to the 0, which is 1, 2 to the 2, which is 4, 2 cube, which is 8, so that's 2. Oh no, for 6 it works. 1, 2, 4, and okay, so for 6, what am I getting? 2 to the 1 is 2.
you're
2,
finding 2 to the 6.
yeah.
It's
So,
64.
no, no, okay, so 2 to the 0 gives me 1, to the 1 gives me 2, 2 square gives me 4,
Oh, the modular
and
value.
yeah, 2,
2 to the 6 would give you 1, I think. Yeah, 63 is a multiple of 7. 64 is
so
what?
this gives me 2.
No, no. Like you're taking modular 7, right?
No, I'm not taking module 6
Oh, modular
because
6.
I want to
Okay.
show that this won't happen for
Okay, okay.
um,
Yeah, got it.
yeah,
For
even numbers.
even numbers.
Right, and minus 2 to the 0 is minus 1, which is minus 5, which is 5. Minus 2 to the 1 is minus 2, which is
4.
4 and minus 2 to the 2
Okay,
is
three more to be here. Yeah, I can see that. Mess up three.
yes, yeah, that's missing. Yeah,
So one, two, four, five. Three is not here.
yeah. So
Twelve
2
for
has
six.
what? 4?
Like the argument, like it needs to be co-prime.
Oh, so 6 and 2 are
Case
not co-prime. Yeah,
six and two are no not co-prime, so two is not a generator of like Z
right.
star six. Yeah.
Yeah.
So, but how would you show that this holds for every even number?
Okay. So to be a generator, it's okay. So the least common multiple would be less than the size of the group, right?
Uh, Least common multiple should be less than the size of group.
Okay. So then can 2 generate Z cross K? It can generate Z cross K when the size of the group generated by 2 is K minus 1, right?
Right.
Okay. Now let L be the LCM of 2 and K,
Two and k.
right?
Right.
Then
Okay.
my claim is the size of the group generated by 2 is L minus 1. Wait, do I need LCM or? Oh, wait, no, no, not an LCM. Oh, no, that works for additive proofs. No, no, LCM just works for additive proofs. No, not LCM. It should become 0. Okay, so if it's no, okay, if it's not co-prime, if it's not co-prime, it's not even Z. It's not even in Z cross K. It doesn't have any inverse.
Oh, didn't get that. Like, if it's
Oh,
not
so
co-prime, so
so if it's not co-prime, it does not have any inverse in the thing. So at least in the group theoretic sense, it does not make any sense to say that it's a generator.
okay.
Okay, so in that case, we need to argue that something that's not in Z cross K does not have this property. Okay, okay, but at least when 2 is a generator, this would work, right?
Yes.
Yeah, so uh, K being odd is a sufficient condition. We need to find a necessary condition, right? That's it.
Right.
Yeah.
Yeah.
Okay, let me think about that. Yeah. So I can think it offline and then tell you in the next session. Yeah.
Yeah, it's fine. Like,
Yeah.
you can think online, you can think offline. I have time.
Yeah.
Okay.
Okay, now I need to go to the mess.
Yeah, sure, sure.
Yeah.
Then you take it
Okay.
offline.
Yeah. Okay. So next time we'll also like cover. Okay. So yeah, I think okay. There is no need to cover the remaining questions of this
I think they are mostly recalls.
week 4, week 3, and week 1, right?
Yeah, we next time we
Yeah.
have week three and week one.
Yeah.
The overview of variance theorems proof
Yes. Yeah.
and showing the sufficient condition for
Right. Yes.
2 being a generator of.
Yes.
Uh,
Yeah.
could you frame this one as a question? Uh, the sufficient condition.
Okay. So the condition is this. Mm, when is every number in 1 to k minus 1? When can you write every number in 1 to k minus 1 as a power of 2? Mod k.
So when can you write every number in 1 to k minus 1 as a power of 2 mod k?
Yes.
Okay.
Yeah.
All right.
Okay. Yeah. Bye.
Okay. Thank you. Bye.